Good morning, everyone. Myself, Dr. Noor Muhammad from Indian Institute of Information Technology, Design and Manufacturing, Kanchipuram, Chennai. And I'm going to present today whatever the work we have done related to energy efficient, multiplier-less, approximate integer DCT design, and which is implemented for HEVC. I'm going to present this work done along with Divya Kuchipudi, is a BTech student, and PhD scholar Skanda Deepsita. Outline of my presentation goes like this: a brief overview of approximate computing and background of the discrete cosine transform and existing approximate DCT architectures and proposed approximate DCT results, and followed by conclusions and references. So approximate computing is there since a long period, but we used to approximate at various levels. Earlier, we used to do approximate at the algorithmic level or implementation way of implementation level or architecture level. Today, we are doing approximation at the hardware level with a major motivation of reducing the energy. As you know that energy is the one of the key component that we have to reduce when it comes to the VLSI chip design. So many of the people are now looking towards the application tolerance towards the error versus my energy consumption. So this is the trade-off they are doing, and with respect to that, they are proposing a approximate hardware circuit such a way that we can reduce the energy. So if you look at the designs today, if you look most of the applications, whatever we are using, it all uses, it will have some level of error tolerance is there. Example, image processing applications, some of the signal processing, video processing applications, even error present in the somewhere, it is not going to impact the output visual quality. At the same time, word processing or even search engines. Okay, so there is some error, it is not going to impact much. So it means approximate is allowed, means accepted in majority of the application, and it is also observed that around 80% of the workload of the any application can be approximated. As a result, overall energy of this chip what we are building, it can be reduced. And other requirement, if you look at, as you know that ubiquitous computing is becoming popular, and many people have started using a portable devices, and these portable devices are operates on the battery powered power. And so if you are running a intensive algorithms on these portable devices, your battery get drains out. So we should have a mechanism such a way that we can save the battery life. In that case, approximate hardware-based computing is one of the solution which can save the energy. And another point of view, if you look at most of the battery technology, whatever we are using today, it doubles every 10 years. Okay, it's a long period. And here is the architectural solution, hardware-based solution to compensate this technological trend. And another point of view, if you look at huge workloads, so whatever we want to compute when it comes to the AI, ML kind of workloads, this can be approximated, where we are finally boiled down to the decision whether it's going to be prediction is where we are going to predict the values. Okay, even a certain number of error present in that, it is not going to impact the output. So, and another important aspect why we have to think about approximate based hardware computing is technological scaling. As you know that we are able to, as Moore's laws continue to implement out. So where today we are putting more number of cores in the same chip, and we come to a state that where around 50% of the dark silicon present on the chip. When you go implement for 8 nanometer technology. So it means we have a hardware, but we cannot turn on because of the peak power dissipation issues. So here, what in this presentation, since we are talking about discrete cosine transform, there's a 2D discrete cosine transform expression you can see here, and where you have a f is the computed discrete cosine transform value, and f of is the input matrix which we are going to give here. And since we are applying a DCT on the image in order to see at the output level, so we need also a inverse DCT. So that also we are going to compute it f of m comma n by using the DCT based whatever the output we get it. So these are expressions for the DCT and inverse DCT coefficients in DCT transforms. Okay. And if you look at this discrete cosine transform, we can represent as a f equal to d into f, where d is going to be a coefficient matrix. As you can see here, it is shown in the diagram. It's a coefficient matrix. And this coefficient matrix, when it comes to the 8-point discrete cosine transform, it can be represented here as it's shown here. Where x0, x1, x7 is going to be the inputs, input signals, and W0, W1 is going to be the output. And what you see here, D, A, B, C, D, E, F, G, these are all the coefficients of the 8-point integer DCT. And when you talk about 8-point integer DCT, its values are going to be, you can see A is 89, B is going to be 83, C is going to be 75, D is at 64, and E is going to be 50, and F is going to be 36 and 18. So now, if you look at, we can substitute these values in this matrix, and where we can also decompose this matrix into a two matrix. One is going to be an even decomposition matrix and odd decomposition matrix. By decomposing that, what are the terms that comes into the even decomposition? Only 3 terms will be present: B, D, and F only will be there. When it comes to the odd decomposition, you can see that A, C, E, G, these are the terms only will be present in this odd decomposition part. So by doing this way, my hardware complexity, I am going to reduce it in the computation process. So now if you look at the existing techniques from the literature, so this is the one work, energy aware computation driven approximate DCT architecture for image processing, presented in 2015. So what they have done is they have taken F as a reference, okay, F as a reference with respect to the F, and rest of the things they have computed. So G is going to be F by 2, and E is going to be 3F by 2, and C is going to be A minus F by 2, and B is going to be 5F by 2. This is how they made it everything in terms of F by 2. It means if you compute F by 2 and the rest of the things, you can able to implement it. And that's the implementation. It is shown in the right side of the architecture. On the same lines, when this implementation, when you put together, this is a hardware architecture that is going to be looked, and where they have completely eliminated W5, W6, W7 in this implementation. Okay. So now let's move on, because all these 3 things they have equated here. That's the reason why they eliminated, because its values are going to be like this. Okay. So now the other work you can see here, other existing work is going to be an energy efficient approximate DCT wireless capsule endoscopy application that is published in 2018. So they have done whatever the A, B, and C values they represented in terms of F and E, and they designed their hardware in this way. So multiplication in 1D. They are doing by using DCT with optimized DCT coefficient they are performing here. So this is the work, and this is the hardware they are using, and they are also using one more level of approximation. That is, they are using a they have in implementation of a 18-bit adder. They are using a lowest 6 bits are approximated, and they are only using a MSB 12-bit based adder. So that's the thing what it is shown here in this architecture. And now coming to that, what we are proposing here, we are proposing a multiplierless approximate integer DCT. The proposed DCT uses approximate coefficient in terms of coefficient. As a result, hardware complexity significantly reduces, and we also applied this one for the image processing, and where we got a acceptable PSNR value, and output visual quality has not been degraded when we apply this one to the hardware. So what is the idea here is, so you can see that we have grouped that all the coefficient in terms of in the 3 groups, 1, 2, 3, where first one is E, ASC is going to be the 8975, and D is going to be 64, 83, 36. Now you can see that whatever the coefficient values are there, we have found it's equivalent 16 multiple of coefficient. That is the thing you can see here. 50 equivalent is going to be 48. That is going 16 by 4. You can make it. Okay. Yeah, sorry, 50 equivalent 48, this is what we have created, and 89 equivalent is 80, 75 equivalent is going to be 80, and 64 is going to be a 64, and 83 equivalent is 64. So this is how we have approximated our coefficient here, and 18 is equivalent to 16. And so what is the idea is we want to have our coefficient should be multiples of 16s. Okay, so the way 16 by 3 is going to be a 48, like that. And that's the thing what we have put it in a even decomposition matrix. You can see here, and now we have a 32 and 64 only is present. Now I'm removing the 64 outside. I'm taking a common of 64. You can see here, this is a matrix which hardwarely I'm implementing in this way. So here we don't have any kind of multiplier. We are only using adder and subtractor and shifter modules. And coming to that second implement odd decomposition, the coefficient values are 80 and 16 and 48. And here we common 16 and you get these values. Again, we have done one more level of approximation. Wherever if I 5, these are all we approximated to 4. And now we make a common of 16 by 4 is the common, which we have made it. And rest of the things we have implemented in the hardware in this way by using a adder, subtractor, and multiplier. Without multiplier and shifters only we have used. And when we implement this one by using, we model all the designs by existing and proposed designs by using Verilog HDL, and we have implemented, we are synthesized by using a 45 nanometer technology library. And you can see that we have compared our designs with the existing conventional DCT and decomposed. So where they are using 64 multipliers, 32 multipliers, and additions are going to be 56, 24 like this. But our proposed only uses adders and 3 shifters. That's the hardware. And we also compared our designs with the different way of implementing a DCT with respect to the accurate point of view. You can see that the proposed design has a minimal area and minimal power it is going to consume, and timing also is going to be very minimal. Similarly, if you, we have compared our proposed design with the existing works from the literature, where you can see here our area is going to be very less power and timing, and especially you have to compare with respect to the power delay product. So where you can see that our power delay product is going to be very less when compared to the existing designs. And you can see from this power delay products of the other DCT implementation, we are getting around 75% improvement when compared to the existing designs. So we also applied this one for the image processing, where we have computed a SSIM and then PSNR value. So this is the accurate PSNR value, and this is the approximate PSNR value. Typically PSNR value 30 plus above is going to be acceptable. And you can also see that output visual quality of this Lena image and this one is going to be acceptable in nature. This is the accurate based computed DCT, this is approximate computed DCT. There won't be a much difference in the image output visual quality when we have gone for 256 by 256 image. The same thing we have done it for the 5112 by 5112, and where we got improved PSNR values, which is be acceptable in nature, and even SSIMs are going to be structural similarity index matrix also is going to be in acceptable nature. And in this work, we have proposed integer DCT coefficient, which we have approximated. As a result, we have eliminated the complete use of adder. We have entire design is implemented by using adders and shifters, and where we have reduced the 77% power delay product in the proposed design. And when it comes to the existing designs like reference number 12 and 18, we have reduced the power delay product that is going to be 50% and 35% respectively. And whatever the PSNR value we have computed, it is an acceptable nature for both the different sizes, 256 by 256 or 512 by 512. So this way it is going to be implemented. And these are the list of references that we have used, and we want to acknowledge that MIT for sponsoring this project. Thank you.